بسم الله الرحمن الرحيم. الحمد لله والصلاة والسلام على رسول الله. Yes, let's continue inshallah our discussion about chapter 1. قبل ما نبدأ كيف حالكم يا شباب؟ إن شاء الله أموركم مع البلاك بورد كلير. طبعا عملت سكشن للجميع ووضعت فيه المحاضرة الأولى. Did you see the first lecture or second lecture actually, because first lecture was not recorded?
Yes, we can see it.
طيب.
That's for me. You didn't add me for the comment section.
You may be added today. هذا بالنسبة للبلاك بورد I don't add you. The university add you, so maybe it's not updated. It will be updated today. It's available inshallah.
Okay, thank you.
Okay. I'd like to ask you before I start discussing the chapter, please put your mic mute, please, all of you, so that if you want to talk or anything, raise your hand or make a sign of raising hand, and then I'll allow you to talk, because it causes some problems when the mic is on. So please put your mics off or on mute. All right? Okay. The last thing I talked about last time was actually the significant figures, and we will continue the discussion about significant figures by saying what do you mean by significant figures? What significant means? Significant means important. No, please don't talk. I'll talk, but I just this is the way I teach. But significant means important. You have to be careful about this. Important, or it has meaning. That's the meaning of significant. It has meaning. All right, good. Now, I told you that when you write any number, we like to write it in the scientific way. This means we like to have the scientific notation like this, and we have a decimal, and usually the best way to write numbers is to write 1.783. You put a number which is non-zero here, non-zero, between 1 and 9, and only one number. That's the best way to write the numbers in significant way. But it's okay to write it 0.321, for example. That's also acceptable. Or, for example, 7.123, 27.123. All of these are acceptable. But the best way is to write only one digit, like, for example, 3.12 or 12, and then you multiply by 10 to the power whatever. If it is 1 or 2 or 3 or whatever, that's the best way to write the numbers. Now, what do you mean by significant figures? Which numbers are significant? Any number that you write other than 0 is always significant. It must be significant. So if you write how many significant figures here, there are 3. How many significant figures here? There are 5. How many here? There are 4. If I write 3.21000, how many significant figures here? All the zeros are also significant if there is decimal point. So in this case, 1, 2, 3, 4, 5, 6 significant figures. So if there is decimal, any zeros to the right is always significant. If the zero in the middle, for example, if I write 3.10001, How many significant figures also here? We have also 1, 2, 3, 4, 5, 6. 6 significant figures. Why? Because the zeros are in the middle. If the zeros are to the left, then how many significant figures here? Only 2 significant figures. Or let's say, so 1, 2, 7. Only 3 significant figures here because the zeros to the left are not significant. Clear? Very good. Now, so if there's any number other than 0 is always significant. Any number, if it is 0, then if it is to the right of the decimal point, this is the decimal point. If it's to the right of the decimal point, then it is also significant. That's why, how many significant figures here? We have 6. If it is in the middle, the zeros are in the middle between numbers, they are all significant. So 3.10001, there are 6 significant figures. All right? If it is to the left, whatever the numbers are, then if there is no number before it, then it's not significant. Now, if there is no decimal point, for example, if I write 5001, then is this significant or not significant? They are significant also because they are in between numbers. If they are in between numbers, they are still significant. If they are to the left, then they are also non-significant. So how many significant figures do we have here? 4. How many significant figures do we have here? Only 2. Only 2. If it is to the right, for example, 50, then I cannot say if it is significant or not significant. The answer is it's not clear. Is this 1 or 2 significant figures? I don't know. I need to put the decimal. If there is no this decimal, then we will say it is ambiguous. Ambiguous, not clear. Ambiguous. Ambiguous means not clear. And that's why it could be 1, or it could be 2, or if there are more zeros, then it could be clear. That's why, let's very quickly solve how many significant figures here without talking. Raise your hand now, let's see if okay, how many significant figures we have here? Okay, you may answer, anyone. Open your mic and answer.
3.
3, very good. Okay, anyone? How many significant figures here?
4.
4.
4. How many significant figures we have here?
3.
3.
How many significant figures we have here?
4.
4.
4, 3, and 4. How many significant figures we have here?
Ambiguous.
No,
3. 3.
4.
no.
4.
4. The 0 is not significant, but these are all significant. 0, 1, 2, 3, 4. All right. How many significant figures here?
Ambiguous.
Ambiguous.
Ambiguous. This means it could be 1
1
or
2.
here. Very good. If I write a number
الدكتور
0.0001 2 0 0 0 1 3 0 0 0. Which zeros are significant and which zeros are not significant? Are these zeros significant?
Yes.
Yes. Why? Because
after the non-zero number.
after the decimal point. Okay. But are these zeros significant?
Yes. Between
Why?
the numbers.
In numbers. Are these significant?
No.
No, they're not significant because the decimal point in this side.
دكتور
Is this clear?
No, دكتور.
Very good. Please put your mic mute again. All right. Now, when we want to add,
Doctor, I have a question.
oh, go ahead.
Doctor, can you go back? Yeah, what is the difference between A and E? Why
A-
we say 3 and in E say and big
A,
ones?
is there any zero?
Sorry?
In A, there is zeros.
Oh no.
Then how many significant figures?
Oh, okay, 3. And
Three.
the E. Okay.
But the problem is only with the zeros. If there are numbers, no problem. Only the zero is a problem.
Okay.
Okay, clear?
Clear.
Significantly, do it this way. Look carefully at the example here in front of you and do it exactly the same way like here. What? Put the decimal under each other. Look at the decimal. They are under each other. Is this clear? Next, count how many after the decimal. Only after the decimal. How many here? I want you to answer. Put your mic on and answer. How many after?
2
2. How many after decimal here?
3.
3
3. Okay. Then your answer should have the same like the least. The least after the decimal. So how many significant figures we have here?
3
3. But how should you report it?
2
Only 2. Only 2. That's why you should round it to 73. Is this clear?
Yes.
Very good. So that's how you add or subtract number. Don't forget, put the decimal under each other, the decimal under each other, and then add normally, use your calculator, then count the numbers only after the decimal, not before, only after the decimal. And count the number after the decimal. And your answer should have the same number like the least. If there is 2 and 3, your answer should have only 2. Next, how many significant figures to start with the whole number? How many significant figures we have here? 5. How many significant figures we have here? 3.
3
In this case, how many significant figures your answer should have?
6
This is the correct answer.
5
In this case, how many significant figures?
5
5. 1, 2, 3, 4. Is this clear? That's how you add or subtract numbers. That's how you add or subtract numbers. But if you want to multiply things, same thing here. Okay, do this. We are going to subtract number. What should we do? We write the numbers under each other and put the decimal. Then, which significant figures you should count? Only this one. How many do you have here?
2
2. How many you have here?
1
1. Your answer should have how many?
2
1.
Only
One.
1. Only 1. So you should round it to 123.2. Okay, after you finish, how many significant figures you have in this number?
5.
5. How many significant figures of this number?
3.
3. And your answer, how many significant figures?
4.
4. I hope this is clear. Good. That's for addition and subtraction. But for multiplication, things are different. For multiplication, go ahead and count how many significant figures you have here.
2.
2. How many significant figures you should have here?
2.
4. 4. Your answer should have the same number. Like, look here, we are counting the whole significant figures, not part, the whole thing. Your answer should have only 2 significant, only 2. Why? Because this is the list. And that's why when you multiply this in your calculator, that's the answer. How should you report it? Only 11. Clear? And you should write it 11 point or dot or 1.1. All of these correct answers. So this is correct. This is correct. Of course, 1.1 times 12, what? Ten to power 1. 1.1 times 10 to power 1. Which is the correct answer? This one or this one?
Both.
Both are correct. But which one is better?
Scientific.
The second one is better because of that. Now, do this one. You do it yourself. Okay, go ahead. Divide this number by this number. Do it in your calculator. Next, this is the answer from your calculator. How should you report this? Very quickly.
For significant number.
It's 0.038.
0.0378. 3. It should be 4 numbers. Why? How many significant figures do you have in this figure? 1157.
4.
4. How about this one?
5.
5.
5. Your answer should have which one?
4. 4.
So that's why, is this the correct answer? Yes,
Yes.
why? Because we have 4 significant figures. I hope this is clear. Right. Now, go ahead and solve A quickly. You do it. Are you done?
318.2.
And 2. We got the same answer. Only this, we will stop here.
Yes.
Forget. Why? Because there is only one number after the decimal and one number, 3 numbers after the decimal. And that's why our answer should have only one number of decimal. Good. Do B quickly.
45.73.
45.73. Is this the correct answer? Everybody. Again, I care about this one and this one. And the answer should be 2, exactly. Do 3 quickly.
0.299.
0.299. Who got the same answer?
Yes.
Why stop here only? Now we care about the whole number. How many significant figures we have here? 3, and here 4. And then the answer should be only 3. Good. Very good. How about we have D?
7.3.
7.34.
7.34. And yes, why? Because we have only 3 significant figures and 4 significant figures. Okay, now, if you have power like this one, how should you do it? Before you do the addition, make the power the same for both of them. You cannot add them if they have different power. You have 2 here and you have 3 here. Make both of them the same power, whatever you want. Let's have both of them as 3, for example. So if I want to make this power 3, what should be the number here? 4, 6 times 10 to the power 3. Where should I put the decimal?
On the left.
Before.
left of the part.
4 here. So I can put 0 here, no problem, because this is not significant. Okay, plus 4.991 times 10 to the power 3. Now, can I add them? Yes, I can. Why? Because the power is the same. And what will be the answer in this case?
5.537.
5.537 times 10 to the power
3.
3, because everything is 10 to the power 3. And now, is this the correct answer? Now you look at how many significant figures you have after the decimal in this case? 3. And here? 3. The answer should be also 3, and it is correct. Is this correct? Is this clear? Very good. Now, last thing I want to say, if you have what's called exact number that you don't measure. For example, if I ask you how many fingers in your hand, how many fingers in your hand?
10.
In your hand, one hand.
5.
5, right? Nobody will say. Can you say it is 5.1? No, never.
No.
Why? Because this is our exact number. You are counting 1, 2, 3, 4, 5 fingers in your hand. But if you have exact number, if I say how many students we have in the class, we will say there are 130 students. Can anybody say 130.1 or 0.15? No, it is 130 students. When you have exact number, like this number, then you don't count it when you do any multiplication or division. So if I multiply 3 times 2.5, where 3 is exact, then how should I report the answer? I should report it 7.5. Why? Because there are 2 significant figures here, and the answer should have only 2 significant figures here, and I'm not going to count. You say there's only 1 significant figure here. I say, no. If you have exact number, you don't count the significant figures. It's exact. It's not significant or not significant. It's not important or not important. It is correct, same thing. So let's give you a very quick example. If I give 10 students, I give each one of them 3.2760 gram of something. Then what's the total grams all the students have? How should you report it? I said I have 10 students. If I say 10 students, what does that mean?
It's an exact number.
Exact number. Don't count it. So you multiply 10 times this number. What's the answer?
32.
760 gram. How should I report it? Exactly the same. Why? Because there are 1, 2, 3, 4, 5 significant figures. How many we have here? Also 5. And since we have 10 students, I don't count the students because it's exact. Is this clear?
Yes. Mr.
See, I told you to solve this question. We'll change it to, but in the solution, in the book, they put it 2, change it to 2, which is the same thing, But as I said, you must have the same power and then add the numbers normally and then count how many significant figures you have in both of them.
Doctor. The answer is 4 significant figures.
Yeah. In this case?
Yeah.
Yeah, it is 4 and 4.
It shouldn't be 2 because the addition.
It is 2 after the decimal. That's to do the addition and subtraction. But after you're finished, then you count the whole significant figure for the whole thing. It is 4, and it's still 4 here. It was 2 when you did the addition. That's why, see, there are 2 here and 2 here, and the total is still 2 here. Okay, but
Yeah.
if we finished, we count the number, and now it is 4 significant figures. Right?
Okay. Yeah.
And
Right.
2 after the decimal. 2 after the decimal, but the whole number is 4 significant figures. Okay, good. Okay, very quickly, let's solve this problem. We have a box container. It has, with volume, this is the volume, and it has this mass. Quickly tell me what's the density. Okay, so we have here, we have a box, that's the volume of the box. What do you have here? This is the volume. Now, so we have a box here. This is the mass of the box when it's empty. This is the mass of the mass of the container. That's the volume. That's the volume of the container, and that's the mass. The container gas, the mass with the gas is 126.5. What can you calculate? The mass of the gas. Go ahead and count the mass of the gas. This is the mass of the container empty, and this is the mass with the gas. So what's the mass of the gas? Quickly, I want an answer.
1.9 gram.
1.9 2 1.2. That's correct.
No, 1.9, just 1.9.
1.9 without 2. Yeah. And how should I report it? Only one significant figure after decimal. Correct? Okay. Now, determine the density. Divide 1.9. Divide by what?
The volume.
It is 9.850 times 10 to the power 2. And you should have the answer.
1.9.
What again?
1.9 times 10 to the
1.9. Give me more numbers. 1.9 what?
times 10 to the power of minus. It's only 2 significant figures.
1.9 times 10 to the power
Minus 2.
minus 2 gram per liter. Is this the correct unit? Why? Yes, it is correct because it's gram and this is centimeter cube, and centimeter cube is milliliter. So whether I write it gram per milliliter or centimeter cube is okay. And there is only 2 significant figures here because there is only two significant figures here, and this also.
Isn't minus 3 to the power minus 3?
Okay. What again?
Isn't 10 to the power minus 3?
No, why? I don't know.
That's what I have.
The calculator.
Yeah, I think it's -3, doctor, because
That's all.
So-
The answer is given to me is wrong. This is the right answer. Yes, it's 1.9 times 10 to the power minus 3. Exactly. You're absolutely right. So this is wrong. Somebody told me it's -2 and I kept it as is. So it is minus 3. Very good. All right. Next, very important. Look carefully at the three boxes here. I want you to know two words: accuracy and precision. First one here, if I ask someone of you to throw this paper inside the basket here, okay, this student is accurate and precise. Okay, this student is not accurate okay, and not precise. Is this clear? How about the student? Tell me, what is he?
Precise, but not accurate.
Exactly. This student is precise because he's always throwing in the same place. So that he's always precise, but not accurate. Is this clear? That's the meaning of precise and accurate.
Doctor,
Yes.
can it be accurate but not precise?
It could be if it's the average, but this is by chance. If he's accurate but not precise, this means he's doing bad job, but by averaging, he got the same, the correct answer. Look at this example, for example. If the answer is 0.3, if I give you this, we have three students giving measurement for something, all right? And I know the correct answer to be 0.375, all right? Then what's the student A? What is he? Student A.
Precious, not
accurate, but precise.
Precise but not accurate.
Yeah.
The accurate answer. The accurate answer is 0.37, I think 1 or 2. Okay, I want you to tell me, how about student 1? If the correct answer is 0.371, is the first student, is he correct?
Precise but not accuracy.
Exactly.
It's precise but not accurate.
Precise, but not accurate. Not accurate. How about student 2?
Not precise.
Not precise, not accurate.
Not precise. Look at this number, 0.373. Not precise. And probably not accurate. How about the last student, C?
Precise and accurate.
Precise.
Look, the answer is around 0.371, so it is actually precise and accurate. Now, last topic I will talk about here, very quickly, I will say this one. if you have any numbers like these numbers, or if you want to change something from something to some, this is called dimensional analysis, or very important word, dimensional analysis. What do I mean by dimensional analysis? I'll tell you what do I mean. If you have two equality, for example, everybody knows that if I have 1 inch, it's equal to 2.54 centimeter. And in this case, I will consider the 1 inch as accurate because I'm telling you, if I have 1 inch, exactly 1 inch, it will be 2.54 centimeter. But now this one is exact, but this one is measured. So if I ask you how many significant figures do we have in this number, what are you going to say? It's 3 significant figures. But if I ask you how many significant figures are in this one, you should say no, that's exact number. We don't care about the significant figures. Is this clear? Good. Now, when you have equality like this one, if things are equal, I can put them in fraction. I can put it this way, fraction like this, or I can put it this way, fraction. So if I have equality, don't forget equality, then I can put them in what? Fraction. Please put your mic off. Put your mic on mute. Everybody, put your mic mute. Okay, so we have here equality, things equal to each other, and we have here fraction. Fraction means one above each other. I can write them this way or this way. Now, when you want to convert any number from one unit to the other unit, this is called conversion of unit. Conversion of unit. How? If I have 7.26, all right, or yeah, fine, 7.26 centimeter. All right, then how many inches are there in this number? What should you write? You should keep it with units. How? Use one of these equality that contains centimeter in the bottom. This is a centimeter, but this one inch in this bottom. So I will use this one. I will go 1 inch divided by 2.54 centimeter. If I do this, now if I multiply this by this one, what will happen to the centimeter with the centimeter? They will go away. And what is your answer will be? Only in inch. And this way, go ahead, do it in your calculator. 7.26, change it to inch. What's the answer?
2.85.
2.85. And that's the answer. Is this clear? Now, how many significant figures should I have in my answer? Only 3. Why? Because there are 3 here and 3 here. How many significant figures you have here?
None. Exact number.
This is clear. We do the same thing with nano and so on. We know, everybody knows that 1 meter equal to how many nanometers?
Multiply to 10 minus 9.
Minus 9 or plus 9?
Minus 9.
Plus.
Plus 9. Nano is extremely small. Meter is big. So 1 meter equal to 10 to the power plus 9 nanometer. Clear? Okay. How many? 1 kilometer How many meters?
10 to the power minus 2.
10 to the power
3.
3
plus
3
plus 3.
plus 3.
Plus 3. The kilometer is bigger than the meter. How about 1 meter is how many centimeter?
10 to
10 power 2.
10 minus 2.
Centimeter.
Plus 2 plus 2.
Here. Now, if I have 72 nanometer, how many meter is this? What should you do? Multiply by fraction. What's the fraction?
1 meter up in the denominator.
Up and 1 times 10 to the power plus 9 nanometer down. The nanometer will go with the nanometer and we have the answer. Is this clear? This is
Doctor, 1 meter isn't equal to 10 plus 2 to the power plus 2 centimeter.
no. Ah, yes, of course. Sorry, yes, of course. Yes. You're absolutely right. Sorry. Yes, I want to say 1 centimeter is equal to how many meters? Yes, 1 centimeter, how many meters?
10 to the power
10 to the
minus
power
2.
minus 2.
Yes, absolutely right. Thank you. Clear? Is this clear? Now, let's solve this problem. Look at this number. You have two. I'm not going to read the question. I want look at to me and only look at the fractions here. This fraction, this equality, and this equality. What can you do with the equalities? You can make them what?
Fraction.
Fractions. Good. If I have 1 or 2.3 gram gold, AU is gold. How many moles is this? Okay, let's read the question before we start answering. How many AU atoms are there in 5.27 gram AU? Okay, so what should I have here? 5.27 gram AU. And I want how many atoms? How many what? Atoms. Here is AU atom. I want my answer to be with this unit. But what I have at this time is GAU. What should I do to get rid of this unit to make it something else instead of GAU?
Fraction.
I want to make it mole first. What should I do? What's the
1
fraction?
over 196.97.
What should I
One
write?
more. 1 more.
1 mole AU and down
196.97 gram.
gram AU. I'll get rid of this unit with this unit. Am I done?
No, multiply by the second fraction.
1 mole AU and at the top here 6.02 times 10 to the power 23 atom AU. And get rid of this unit with this unit and you have the answer. I want you to do it very quickly in your calculator. Give me the answer.
71.69.
71.69. What? 71.69. No, times 10 to the power what? This is correct. Wrong answer. What's the answer? 5.27 divided by 196.97 times 9.02 times 10 to the power 23. What's the answer?
$71.7.
Multiplied by what? Must be something.
I got 1.61 multiplied by 10 to the power 22.
I don't know what's the answer, but this looks more reasonable.
Yes, it's correct.
Times 10 to the power 1022. I don't have the answer. I put the answer for you. Look, this question is actually from chapter 3. It's not from chapter 1. Now we are solving problem from chapter 3 without understanding anything. We did not talk about the mole. We did not talk about Avogadro's number. We did not talk about the mass of a mole. All of these things are available in this question. And now you are solving question from chapter 3 without even understanding things. Why? Because you are using the very good method of dimensional analysis or conversion of unit. Conversion of unit. You are converting units. Is this clear? I hope this is clear. And with this, we actually finish chapter 2. Sorry. We finish chapter 1. And we will start right away chapter 2. Okay. Okay. Now we are in chapter 2. Bismillah ar-Rahman ar-Rahim. What's the title of chapter 2?
Atoms, molecules, and ions.
Molecules and ions. Good. Is this clear? I want you to know. Everybody knows what's an atom. Give me an example of atom.
Helium.
Sure.
What's this?
Iron.
Ion. Sodium.
Sodium.
Potassium. Oxygen.
Hydrogen.
Hydrogen.
Give me example of molecules.
H2. O.
H2. O.
N.
PCl3 and so on.
O2.
NH3. O2 is a molecule, but it's atomic molecule. Okay, good. Give me an example of ions. Do you know what are ions?
NaCl.
No? Ion. Na.
Ammonium.
Plus.
Na plus.
Cl minus.
What?
Cl minus.
Cl minus. Give me another example.
Fe plus 2.
F minus.
2 plus. What else?
H4 plus.
O what? O minus.
Al plus 3.
Al plus 3. Thank you very much. All of these are ions. Is this clear? Very good. Now, the first person who talked about atoms was a person called Dalton, and I want you to memorize the name very well. Dalton. Dalton. Memorize the name. It's required. I can ask you in the exam who is the first person who proposed the atomic theory, and you should answer me, Dalton. And what does he say? Say that everything consists of extremely small particles called atoms, and compounds are mixture of more atoms of more than one element are called compounds. So he called elements that contain small particles, which are called atom, and compound contain atoms of more than one element, and he called them compounds. So we know what's called atom and compound. And a chemical reaction is exchange between the atoms. Example, O2 plus H2 to give you H2O. What happened here? the O was bonded to O, and H was bonded to H, and then now the O is bonded to this H and to this H. Is this clear? That's what's a chemical reaction. So the chemical reaction is rearrangement of atoms. Rearrangement. You put them in different places. Okay? Then we will go to another important law, the law of definite proportion. The law of definite proportion. Before we go to this, did you hear about law of conservation of mass?
Yes.
What's the law of conservation of mass? Yes, the law of conservation of mass, if you have any chemical reaction, then the mass of the reactant, the total mass of the reactant, must equal to what? The total mass of the product. What do I mean by this? If you take the same reaction, H2 plus O2, and you have complete reaction to make H2O, then the total mass of H2 plus O2 must equal the mass of the H2O of the product. So we need to balance this to this one. Is this clear? What's the name of this law?
Conservation of mass.
Conservation of mass. That's the law of conservation of mass. Now we have another law, law of definite proportion. No law of definite proportion. What do I mean by that? If you take carbon, this is carbon atom, and you react it with oxygen, and you make the compound CO2. Okay? What did you do in this reaction? You react oxygen, O2, with carbon to make CO2. Clear? Now, the mass of carbon to oxygen in this element, they take the mass of the carbon only, and they found if the mass of the carbon to 333.6, then the mass of the oxygen in this compound is 89.4. What's the ratio? It is 2.66 of oxygen to 1 gram of carbon. If you take another compound, if I take 13.8 gram carbon, reacted with oxygen, I will find the mass of oxygen 36.7. Then what's the ratio of this one to this one? It is 2.66.1. If I take 24.2 gram carbon in here, and then I calculate the mass of oxygen in here, I'll find that it is 64.4. What's the ratio? 2.66 divided by 1. How can I get this ratio? I divide this number by this number, this number by this number, this number by this number, and I got this ratio. What do you notice in this ratio?
It's the same.
So the ratio of oxygen to carbon in any CO2 compound is always the same, definite. That's the law of definite proportion. Is this clear? I repeat one more time. If you take the mass in any CO2, the mass of carbon and the mass of oxygen, divide them by each other, you will find that they're always 2.66 to 1. Always. And that's called the law of definite proportion. I hope this is clear. Now, why is this? Now, we know that what's the mass of carbon in our periodic table? Now, what's the mass of carbon in the periodic table? Do you know? What? 12.01. In the periodic table, you have the periodic table?
Yes.
Yes.
Okay, look at the periodic table, look at the mass of carbon, it's 12.01. What's the mass of oxygen? What's the mass of 2 oxygen?
16 for oxygen.
What's it for 2 oxygen then?
32.
32.
32. Divide 32 by 12.01. Go ahead, do it in your calculator.
$2.66.
2.66 to 1. So the ratio is always 2.66 to 1. Is this clear? Same ratio like in here. Is this clear? Very good. Let me ask you another question. If I have this compound, CO only, is the ratio going to be 2.66 to 1?
No.
No. What is it going to be? Go ahead, do it in your calculator.
$1.36.
So it will be 1 to 1.33. Exactly. So if we change the compound, then we cannot apply the law of different proportion. The law of different proportion is only for the same compound. All right? Again, I repeat one more time. The law of different proportion. In any compound, like for CO2, the ratio of carbon to oxygen is always constant. The ratio in CO2 is always 2.66 to 1. If we have another compound, like for example CO, then the ratio is different, but it's always also constant. It is 1 to 1.33, the ratio. Is this clear? What's the name of this law? Law of definite proportion. Law of...
Doctor,
Yes.
how did you calculate the ratio?
Divide the mass. This is the total mass of oxygen. Divide by the mass of carbon. Divide this by this. Divide this number by this number. And you'll get the ratio. In another compound, this number was the mass of oxygen. This number, the mass of carbon. Divide this one by this one. And divide this one by this one. And divide this one by this one. And you'll get the same answer. In a third compound, this is a compound, and this is the mass of carbon. The ratio is always 2.66 to 1 in CO2. But if you change the compound, if you make it CO, then it will be 1 to 1.33. This is called law of definite proportion. I hope this is clear. Next. Okay. Now, what's the ratio of, do you have periodic table? We need to have periodic table. What's the ratio of sulfur to oxygen in SO2? What's the mass of sulfur from the periodic table?
32.07.
0.07 or 8? Yes, 7. Very good. What's the mass of oxygen? This we got from the periodic table, 16.00.
16.
Exactly, from the periodic table. You need to have your periodic table with you all the time. Clear? What will be the ratio of sulfur to oxygen in this compound?
2.00375.
2.004.
1.02.
1 to 1. Why?
Because we have 2 oxygen.
Exactly. Okay, if we have another compound, SO3, what will be the ratio?
One, two.
0.66.
What?
0.66.
Yes. No, I want the oxygen at the end.
1.5.
Exactly. So it will be 1 to 1.5. This is sulfur and this is oxygen. So yes, it is 1 to 1.5 in this compound and 1 to 1 in this compound, and that's called the law of definite proportion. If we have another law which is called multiple proportion, okay, we found in CO2 the ratio is 2.66 to 1, 2.66 to 1, 2.66 to 1. That's in CO2. But in CO, the ratio is 1.33, 1.33 to 1, 1.33 to 1, the ratio of oxygen to carbon. The law of multiple proportion says that if you have two compounds, in this case, what are the compounds? CO and CO2, consisting of only two elements. How many elements this compound consists of? Carbon and oxygen. How about this one? How many elements?
Two.
What are they? Carbon and oxygen. Then we have, for each one we have definite proportion like this one. So if we take the amount the ratio that reacts with 1 gram of this one, which is 2.66, to the amount of this amount that reacts with 1 gram, which is in this case I will take 2.66 to 1.33, then what's this ratio? 2 to 1, and it is simple ratio. So if we take the amount of oxygen that react with 1 gram of carbon to the amount of oxygen that react with 1 gram of carbon, in this case, then this ratio, which is 2.66 to 1.33, must be a simple ratio. It must be 2 to 1 or 3 to 3, 3 to 4, or things like that. And now we can see this same ratio. Look at this ratio. What's this ratio? 2 to 1. Did you see these numbers here? Look at this one. 2 to 1. Is this clear? So let me give you an example. I have SO2 and SO3. We just did this a while ago. What is the definite proportion of this compound? We did it just a while ago.
1 to 1.
1 to 1. You remember this or not? Yes, this is 1 to 1. How about SO3? What's the ratio?
1 to 1.5.
1.15. Now, what should I do to calculate the multiple proportion? I should take the number that will react with 1 gram of this one, and the number that will react with 1 gram of this one, and you should write them above each other, 1 to 1.15, 1.5. And is this a simple ratio?
2/3.
2/3. Did you see this number in the compound? Look at these numbers, 2 and 3. Do you see them? Did you see them?
Yes, Doctor.
Yes.
Yeah. So the proportion is actually the ones that are available in this company. Is this clear? Very good. Now, let me give you another example. If I give you P4 or P4 CL6 with P2 CL5. Okay, now Okay. Now, what do you expect the ratio of Cl to Cl if we have a complete compound? Now, before you do the ratio, you must make the amount that will react with P is the same. So I will make this P4 Cl10. Why? I want this 4 and this one 4 also. Then what will be the ratio in this case of Cl to Cl in multiple proportion?
3/5.
What?
3/5.
Exactly, 6/10 or 3/5. Is this clear? That's the multiple proportion. So the definite proportion, we do it for how many compounds? How many compounds? Definite proportion, only one. Clear? But in proportion, we do it for 2 compounds. 2. Is this clear? Okay. Now, water consists of H2O and H2O2. Okay. What's the mass of water? Okay. We found that in water, okay, in water, this is in water, H2O, we have 0.125 gram of hydrogen for 1 gram of oxygen. So in water, we have 0.125 gram hydrogen with 1 gram of oxygen. So what's the ratio of hydrogen and oxygen in water? What's the ratio? 0.125 to 1. In hydrogen peroxide, which is H2O2, this is called hydrogen peroxide, the ratio is 0.063 gram of hydrogen to 1 gram of oxygen. So 0.063 to 1 oxygen. Then what's the ratio of hydrogen to hydrogen? What's the simple ratio? Go ahead and calculate it. What is it?
Sure.
0.125 divided by 0.063. It's actually 2.
Dexter, you are muted.
What's the name of the person who proposed the structure of atoms?
Dalton.
Dalton, exactly.
Dalton.
So we have Dalton.
Dexter, can you repeat the last law in the last 5 minutes?
No, I have to go. You can come up. You stay after the class and then go back to it. Okay. Now, the name of person who proposed the structure of atom is Dalton. Dalton. Don't forget the name. Very important. Then another person called Thomson. You have to know this name as well. J. Thomson. Memorize the name. Okay? He did an experiment I want you also to name the experiment. The name of the experiment is cathode ray. Write the name. Cathode ray experiment. Cathode ray experiment. What did he do? He put one element as the cathode and another element, the same element in this side as anode. So this is the cathode and this is the anode. And this one is called cathode. And he had this tube empty of air. There is no air in it at all. All right. Then he put electricity on this thing, and he found that there's something moving from this side to this side, even though there is no air at all in the tube. So, you know what's the meaning of evacuated? Evacuated means nothing inside, no air at all. Evacuated, evacuation. All right? So even though there shouldn't be anything in this tube, he found something is moving. And that's the experiment another way. See, he put this one electricity, this electricity here, and he put a cathode of gold element and an anode, and when he put electricity, he found something is moving. And then when he put a magnet like this, he found that this green line that's moving is actually going toward the magnet, like this one. And if you put the magnet from this side, he found that the thing is going to this side. The name of this experiment is called cathode ray experiment. And the name of the person is J.J. Thomson. You must memorize these names. And in this case, he found that the atom consists of electrons. So he said that the atom consists of electrons. And he was able to calculate the mass of the electron to the charge of the electron, E to C, to M. E to M. I want you also to know. So what I want you to know from this slide. What's the name of the author, of the person? Thomson. What's the name of the experiment? Cathode ray. What did he find? Or what did he propose? That the atom consists of what? Electrons. What did he calculate? He calculated the E to M, which is called, look here, charge to mass of the electron. E to M, charge to mass. I want you to memorize E to M, and this is the charge to mass. He found the charge to mass. And another person, I want you also to know the name. This is called Millikan. And he did another experiment. I want you to memorize the name. Don't forget to memorize the name. Millikan. This is the name of the scientist. The name of the experiment is called oil drop experiment. Oil drop experiment. I want you to memorize the name, in which he put some oil drops like this, and he made them go through barrier like this, and he was watching it with X-ray, and he was able to find the charge of the electron, E, which is charge of electron. Now, what did Thomson discover? You remember Thomson?
E over M.
E over M. What did Millikan calculate?
E.
E. So what can you do?
Find M.
Find M. And this is the mass of the electron. So these two scientists together found the mass of the electron and found the charge of the electron. So by these two scientists, they were able to find the mass of the electron and the charge of the electron. Then a third scientist, which is called Rutherford, he did an experiment, a third experiment, which is it's called gold plate. You have to memorize the name. Gold plate experiment. Okay, in the gold plate experiment, he found that the atom is actually, he was expecting that the alpha ray will go through, but he found that it was deflected like this, and he said that the atom consists of nucleus in the middle, and the electron is available in a circle around it like this, and all the mass of the atom is available in the nucleus, and the rest is empty. That is the Rutherford experiment, the third experiment, and he found that there is, he called this one nucleus, which is called بالعربي النواة, and the electron is available in circle, which was the electron proposed by Thomson and Millikan, and then Rutherford said the electron is available around the circle like this. Okay, with this I'll stop the lecture now, and we stop here. I'm happy now. I will stay here for another hour. If you have any questions, you may stay and ask questions, but now the lecture is over, and you may leave now. Thank you. See you, or you may start asking questions. Let me just, before I go further,